연사님 소개하기 전에 두 가지를 먼저 말씀드리겠습니다. 첫 번째는 아쉽게도 이제 그 영어 트랜슬레이션이 이번에는 제공되지 않습니다. 작년에는 제공되어서 좋았는데요. 그 대신 어제 연사분도 그렇고 오늘 연사분도 그렇고 좀 천천히 이렇게 또박또박 말씀을 해달라고 부탁을 드렸습니다. 그래서 특히나 이제 바우디시 교수님은 막 이렇게 말씀하시다고 막 빨라지신대요. 그래서 빨라지면 제가 시간을 하겠다고 말씀드렸고요. 그리고 또 하나는 지금 오늘 키노트도 그렇고 내일 키노트 다 그 촬영을 녹화를 하고 있습니다. 해서 나중에 그 한글 자막을 넣어서 학회 홈페이지에 올릴 계획입니다. 그래서 혹시 이제 이해가 어려우시더라도 다음에 다시 또 들으실 수 있을 기회가 있습니다. 그리고 또 한 가지 말씀드릴 거는 오늘 키노트와 어제 키노트 둘 다 ACM 시그카이 지원을 받았습니다. 이건 영어로 말씀드릴 것 같은데요. This keynote talk, as well as the keynote yesterday, is supported by ACM 시그카이. Let's thank 시그카이. Okay, then let me introduce today's speaker briefly in Korean. 바우디시 교수님은 독일 다음스테트 유니버시티 오브 테크놀로지에서 컴퓨터 사이언스 PhD 학위를 받으시고 마이크로소프트 리서치, 어댑티브 시스템즈 인터랙티브 리서치 그룹에서 리서치 사이언티스트로 계시다가 지금 현재 포트담 대학 파송 플래티넘 인스티튜트에서 컴퓨터 사이언스 교수로 재직 중입니다. 단연간 내추럴 유저 인터페이스, 모바일 디바이스, 터치 인풋 분야 연구를 해오셨고요. 그리고 현재 중점 연구 분야는 인터랙티브 패브리케이션입니다. 오늘 톡의 주제가 되겠는데요. 2013년에 카이 아카데미 멤버가 되셨고 2014년에 ACM Distinguished Scientist가 되셨습니다. The title of the talk today is 5 Challenges for Personal Fabrication. Okay, please join me welcoming Professor Baudish.
감사합니다. I will not try to give this in Korean, but I will try to speak slowly. And whenever I speak too fast, you all raise your hands. Is that okay? Can you do that? Can you try this out real quick? All raise your hands. Okay, I'm speaking too fast already. All right, I'll try. So, I know this is a diverse audience. How many of you are students actually? These? I see. And how many of you actually have a job? You're here for a job because you're actually usability personnel. You make money with HCI. Okay, not that many. Mostly you spend money with HCI. Good. All right. So thanks so much for having me. So I've been a professor at Hasselblad Institute for the past 8 years. As Georg was saying, my background is in interactive devices. I spent many years at Microsoft Research working on creating all types of different interactive hardware, and including touch screens, interactive floors, a variety of different things. And then something like 3 years ago, I got really excited about this, what I think of as a reasonable new topic, personal fabrication. And I'm really excited about it because I think it's everything I always wanted in a research project and more. So maybe today I can get you a little bit excited about this topic as well. And I will try to make it actionable by telling you what I think are interesting things to, open questions, and maybe, one of two of you want to, grab me afterwards and maybe have some answers, maybe want to help me work on these things. All right, so here's a little teaser. This is one of the things I'll show you. We've been working on different software and hardware techniques that allow us to use 3D printers and laser cutters in more efficient ways. All right, there we go. And I need to push this button here. All right, so I'm actually kind of curious. How many of you ever used the 3D printer? Okay, wow, great. That's like a third of you. Fantastic. So for those of you who haven't done this, it's very, very simple. Today, there's a good amount of machinery out there that allows you to make things under computer control. A milling machine, a little more messy, used less often. Is a subtractive tool, removes material. 3D printers are additive material, so you put, essentially it starts with 0 and builds up the object. And laser cutters, kind of almost my favorite, also remove material, cut material up in different parts. If you think about how they implement it, there's a lot of different ways how to implement these things, but essentially you have some sort of a robotic thing, like an XYZ table, some sort of construction that allows you to place a tool in 3D space. Could look like this. And then at the end of this, you mount either a drill, and that's called a milling machine, or you put a glue gun there, kind of the same heat gun that the heat glue gun that you maybe used in kindergarten, or a cutting laser, and then you've made a new fabrication tool. There's lots of other ways of implementing this, obviously, as well. So I think this is really going to change the world, and let me try to tell you why I think that is. So traditionally, when you're having a mechanical problem, you have a mechanical solution for it. So let me show you an example of how this works. So for example, here's an example. I want to make a copy of something. And what I do is, I'm getting myself an analog copy machine. So let me show you an analog copy machine. I don't know if you ever did this, if you lost your keys. I certainly have. So this is the actual original key that you have. And this is a blank key, right? So it looks the same, but it does not have the pattern in the, I guess it's called beard. And so you both put them to the machine. Let me give you some sound of this thing. Sounds like this. And what happens now is essentially this side here is sort of a scanner. You push this into the key, and at the same time you're cutting on the other side, and you're getting a direct copy from one to the other. Right? And I'm sure if you're anything like me, you've lost a bunch of keys in your life. So this is a mechanical tool that creates a mechanical solution for a mechanical problem, but it's an analog solution, and it requires a highly specialized machine. You cannot really, all this thing does is copy keys, actually just a certain subset of keys. Now, how this is changing today is we're moving to a digital model. So instead of directly making a copy, you actually first 3D scan the object, then you do everything you need to do in digital, and then you reprint it, and you get this out. And you might have seen this type of process before. The copy machine that you have at your office, copy machines used to be analog. I used to work for Xerox, so Xerox had this process of copying things. And today it looks exactly the same as your old copy machine, but it actually is a scanner-printer combination. It just looks exactly the same as before. Now, what's interesting about this process is, so in the first place, the same thing comes out. I can still put a cup in, I get 2 cups out. 3D printer, 3D scanner, all fine. The difference between the two methods is the fact that now, in the moment of creating this, I've created a digital cup for a moment. And this digital cup is really what this talk is about. Without this digital cup, I would have exactly what I had before. But this digital cup is very interesting because now we're in computer science land. Okay, so this digital cup goes a long way, and we're going to talk about sharing on BitTorrent and all the things that can happen to the cup. So it enables completely new workflows. Here's one example. One of the early adopters is the car industry, and if you're a proud owner of a 1974 Volkswagen Golf, and if you happen to bump into that bumper, again, if you're anything like me, and you damage the car periodically, you might want to get a replacement part of this thing. And for Volkswagen, that's actually a difficult challenge. They need to give you, they need to have that part. And so when you order the part, you're going to get it shipped from a very remote location, maybe in Wolfsburg, Germany. Someone's going to package this up and send it to you. And you're going to pay, I don't know, $150 or something like this for a piece of plastic. And you're like, what? Why is this so expensive? Well, the reason is that Volkswagen is not interested. They would need to, it's a lot of effort they have just to maintain every single part of every single model they ever made. And this is actually one of the things where fabrication can come in. So rather than actually holding on to these legacy parts and then producing them, small quantities when you need them, you can actually just store the digital model and produce them on demand when you need them. And then in slightly more distant future, this model actually could go to a fab lab close to you. So rather than getting it from Wolfsburg, you could actually get it from the local fab lab in Seoul or wherever you are. And in some even more distant future, this model could actually come to you. You have the 3D printer at home, the model is sent to you, and while you're still under the car fixing things, the model actually 3D prints and you insert it into your car, and you can actually finish things in the same day for much less money. So it's one of the potentials, and the solution I just described to you is a classic database solution. right? This is kind of what computer science does, very different from how mechanical engineering does things. So is it going to be big? I think yes. And here's why. So let me show you the pattern again. Here's this pattern. There's like some sort of you've got some sort of a scanner here, and you've got a printer. You stick in an object, and okay, so you convert it to digital, and then you convert it back to analog. Let me show you this pattern in the past. So you may remember this one if you're, well, not the students, but the rest maybe. You know, desktop publishing became really big in the 80s. Before this, people would kind of make layouts by actually having paper clips, and when you're submitting something to a conference, they want a camera ready. That's because there used to be a camera when they made that ready version of their talk. Today, obviously, there's no camera ready, there's no camera involved anymore, but it used to be. And so, at the time when scanners and printers were available, you could actually solve everything you need to solve in computer science land. That's exactly what happens when you're submitting a publication to this venue here. You know, I'm sure there was no camera was involved in that after that. Here's a different version of that pattern. Music production, right? It was analog. You know, you had like an LP, maybe you still have some LPs, but it became all digital, and in between you have digital distribution. That's kind of why we have Apple the way we have it today. Apple became a media company because of this model here. A lot of things changed. One of my favorites in the 1970s, a guy called Schaub at Xerox, he stole away time at night, and he did this here. He used a tape recorder and he ripped videotape onto a Xerox Alto, and then they painted around in the picture, and then they wrote it back to the tape. People thought it was a tremendous waste of time at the time. People threatened him to fire him for wasting company properties for working on these things. But he actually got an Emmy Award years later because he invented video editing. Okay, so if you think of like, you know, back in the day when MTV actually had video clips, you know, it created a whole new art form. And if you go further back, you know, there are lots of instances of this pattern. You could even go back to as interactive computer terminals. Before this, there was no interacting with computers, and there was a way where you could type something in, and there was a printer on the other side, and somehow you closed the loop, and this made computer system interactive. So the pattern that we see in fabrication today, the presence of a printer and a matching scanner, is a pattern we've seen a lot in computer science, interactive computer science, and every single time we saw this pattern, big things happened. And I think big things will happen again this time. So the world changed. And essentially what happened, this other field, you know, that was scanned and printed, that kind of was sucked into computer science. This might have been a separate field before, like desktop publishing. If you ask someone in the 70s, you know, and they were like a layouter, they would not say, I have a computer job, right? This was a completely separate profession. But then since the 80s, you know, being a layouter certainly became a computer job. You know, new jobs were created, lots of old jobs were killed. You know, huge industrial change happened as a result. So, and what's interesting about 3D printing is it's certainly going to affect things. It's not just one field, it's all the fields that have to do with physical matter are affected this way. So you can think of, you know, this could be like structural engineering, mechanical engineering, everyone who deals with physical matter today will be affected by this. It's actually happening. Let me start with this one here. I kind of like this one. So my student Stephanie kind of dug up how many papers are submitted in HCI graphics conference on the topic. So, okay, so this was until last year, and you can see how the number, like there was nothing before 2011, and then the number of publications has really steadily ramped up. I was in the WIS program committee last time, and I think out of the 40 people on the committee, there were 6 people who said that their primary interest is fabrication. So it's really like happening in a very big way. There's exponential growth in the maker scene. So I like this web page here. They have 200 different 3D printer designs. You can go there. Most of them are royalty free. You just kind of look at the models. You can download them, and you can make your own. You can make yourself a 3D printer. A lot of things happening there. Exponential growth in sales in 3D printing. And I think what's really interesting is that the industry is trying to address other people. So the first 3D printer actually I own is this one here, which cost $50,000. I guess that makes it something like 60 million won. Then the next one I bought was a MakerBot for 3,000. Right, so look at the huge price drop. And this was intended makers, so not professional users anymore, but people who just enjoy doing these things, hobbyists. And then now there's a printer called PrinterBot. This is the cheapest thing. I also don't necessarily recommend it, but it's interesting to see that this can still be done with less money than the previous ones. And so this raised the question if this could go out to consumers. And I just met with Hewlett-Packard like 4 weeks ago, and they're going to put out a new model this year that's the first time that's actually addressing consumers, very deliberately addressing consumers in that space. So I think this is a great opportunity, and I think the great opportunity is to have millions of people make things. So I think that's exciting because it depends on what people make. And I'm an engineer, and I would like them to engineer. I would like them to solve mechanical problems. I would like them to come together, make local adaptations of what they need for where they live, and I would like them to collaborate together in solving bigger problems. And I think there's good evidence in computer science where at the moment lots of, millions of people can work on the same problem together, that bigger problems are being solved. So this is something I'm really excited about. So I think the grand challenge is to let everyone solve mechanical problems, right? The same way that desktop publishing systems let everyone publish and movie editing. I can edit movies on my cell phone today, and I think we're going to see similar things for mechanical problems in the future. So now to get there, I think there's a bunch of different sub-challenges we have to solve. There's still a lot of work in materials. I'm not going to talk about this today. I'm going to show a lot of work on interactivity. I think initially these machines were terrible batch processing systems. They still are. You work on them, you print them out, it doesn't work, you go back. I think one of the key elements is adding domain knowledge when people want to make smart things. I don't know about you, but I know very little about desktop publishing, but I like the fact that I have a desktop publishing software that shows me how to do things. So that's very powerful. That's the key idea of a software system, that it can, what you're lacking in skill, what I'm lacking in skill, the software system can actually add to us. And then we're going to look a little bit more into the future and we're going to talk about sustainability. The moment you make bits, bits go away reasonably easily, minus NSA and so on. But physical matter is actually produced a lot of waste, so we have to think about these things. And the last thing I want to look at is intellectual property. People suing each other over fabrication things. All right, let me jump right in and let's start with interactivity. So this is the only part of German I have in this thing. But so after I said come send me down, maybe you can try this one for me. So this is from a German distributor, AlphaCAN, and it says, alles schläft, einer schafft. Everyone's asleep, only one is working. So they think of this as a commercial for this 3D printer. They want to say, look, our 3D printers are so reliable, when you already have gone home, these things keep working. But what it says to me is, our printers are so slow that when you can already go home, our machines still have to work because they're so damn slow. So I'm not sure that's really a commercial. I'm not sure they're helping themselves. So this is kind of how long 3D printing takes today. If you want to make, a small print, it can be like an hour. There's not much you get in an hour. It's kind of like this size. We could make something bigger. That would take something like, a day. And then people have printed houses and airplane wings and so on. This can take as ever long as you want. So no one seems to mind the waiting, right? It's really slow. Everyone's okay with that. And I think we've seen also that before. If you think about computing, back in the day, computing used to be very slow. So I don't remember this. Like if you're substantially older than I am, you may remember times when you went to a terminal and you had a stack of punch cards. You had your program, you compiled your program, you went to the machine, you dumped it into the machine and tucked the cards in, and then the next day you got a report back that says error in line 20. And then you would repeat the process and you would edit your program and repeat the whole thing. That's called batch processing, and this was done in computing with punch cards in the 50s or something like that. So I don't know if you recognize. Okay, so this on the left is not Ivan Sutherland's Sun operating system though, but here's Sutherland's system, and on the right is obviously Doug Engelbart. So these are key pioneers of interactive computing, and ever since we listened to these people, we realized that computing can be different, right? We don't have to sit there and just send something to the computer and get it back the next day. We can actually interact with computers. And so in our group, we've kind of tried to look at these things for a while now. And we do something we call low-fab. And the thing I showed you earlier is actually kind of an example of what we call low-fab. So we had some idea of how to make low-quality prints. What I just showed you is a low-quality print because it's this mesh there. It's not as good as the actual object. And we came up with a bunch of ideas how we can make versions of 3D print that are not as good as the original really wants to be. And we're like, what are we going to do with this thing? So we could be 10 times faster, but what is it going to be useful for? Many of these objects, they just don't have the same qualities. But then, so we could conceptually get printing to a minute range, but the objects are not that satisfying. So, but then we realized that these things that typically don't, this is not all that happens. People typically have series of designs. So I know many of you are designers, so typically you don't just solve the problem once, you kind of make a solution, then it may not work that well, you iterate a bunch of times. And every single time, you might actually print something out. And so this was a workflow we felt we could actually help with, and this is what we call low fab, or low fidelity fabrication. The traditional workflow was that, you would start with a 3D model and you get everything is high fidelity, and then you're printing again, it's again high fidelity. But we felt like we could actually do better if the in-between steps, they could be low fidelity. So the idea would be that rather than printing, 16 hours every single time, you would make one 3D print that was really nice at the end, and in between you make these low quality versions of it. So let me show you one that we showed at Pi a year and a half ago, called Fabricator. And as you can see, are Legos big in this country? Who played with Legos as a kid? Lego bricks? No? Some of you, okay, good. Okay, this was certainly a childhood favorite of mine, playing with Lego bricks. So let me show you how this works. So I load my 3D model into the Fabricator software, and I say Legofy, and it makes Legos out of them. And in this case, I just want to check the optical path. This is a VR headset, and I just want to make sure that the lenses are in the right location. So I go back in, and I tell these areas around the lenses that they should be 3D printed, and everything else I'm okay with having in Legos. So I'm exporting this as an STL file. That's the standard format, the terrible standard format for 3D printing. And one of the things printing, I can sit down and actually assemble the rest of this thing. And when it's done, I've got my 3D printed parts. They fit in perfectly into the Lego setup. I pop them in, and I can start trying this out. It looks a little funny. We're all going to wear these things in the future, believe me. All right. So, and I can continue to operate. So Lego is highly modular, right? And as a designer, I would like a modular design. So now I can adjust like the headpiece and so on, and it just can go through my process a bunch of times. And when I'm all done, then I'm going to 3D print the whole thing, and I've saved a lot of time. I should update this. So we actually created a webpage called brickify.it. And if you're interested in this, you can check this out. You can actually drop your own STL files in there, it converts them for you, and you can try out this process. And in the software, you can go in and you can tell the system how much, what parts of the model you would like to be Legos, and which parts you're happy with being 3D printed. So Legos were great because they were very modular. We also talked to like the Stanford Teachers Association about using those in class, or in high school. Kids are very familiar with Legos and it seemed like a really good approach. But there were other applications where Legos didn't seem to fit that well, and one of them was ergonomic testing. So if you're working for a company that actually makes a grip, so I'm using this old Logitech presenter here, the size of the shape of the grip is really important for me. So these things are very carefully designed, for example, at companies like OXO. So we wanted to have a fabrication, a low-fab version that actually captured more of the essence of the shape. And this is actually what I showed you earlier called wireframe. So again, it's the same method as before. You can actually go in and say which parts of this you would like to have high fidelity fabricated. So in this case, this is kind of a piece of a bunny here. I can say I want this to be high fidelity and everything else is low fidelity. And again, I'm getting the speed of something like a factor of 10. Not quite that fast yet. All right. And then the last version we actually showed at the last Kai, called Platener, because we're replacing the contents with little plates. So this is actually a 3D model that was designed for fabrication with a 3D printer. And what we did is we kind of said, like, maybe we can convert this to a laser cutter, which fabricates way, way faster. So here's the same model that we converted in a bunch of different ways. The actual model itself takes 16 hours to print. And then all these other versions are different types of low fidelity versions of that headset. And let me show you that. Okay, so the same process as before. You can kind of mark up what parts you want high fidelity, and the rest is converted to these kind of later plates. So that was the idea of low fidelity fabrication. And what we got out was, we got a technique for 3D printing that got us up kind of to the minute range. So you could work with 3D print and you would quickly fabricate like a little test run, see if it fits your hand really well, ergonomics, whatever you wanted to test, and then you could iterate quickly. And so the idea would be that, rather than a single process taking a week where you like print on Monday, print on Tuesday, print on Wednesday, print on Thursday, you would print 5, 6, 7 times in a day, and then overnight you would print for the customer and would be done. So we wanted to push this further, and the next thing we were wondering, can we get 3D, can we get up the interactive rate to like a second range? What would that be like? And so if you believe in my analogy earlier, we wanted to transition from batch systems to the command line. We're still like in the 60s, right? But like rather than like sending out a batch of punch cards, we wanted to interact with the system every, multiple times a minute. So here's a system we built called Constructible. That's my student Stephanie, who is actually involved in a lot of the wonderful work. And we're thinking of the laser cutter as kind of a touchscreen in a way. So I don't know if you can see this here. There's a laser. When she points, she actually gets like a red dot here. There's a camera system above that tracks what she's doing. The system beautifies things and then refabricates with the actual built-in laser. She has 20 different tools. One of them only extrudes, one of them only makes rectilinear contents, and you'll see a couple of things. This one is one that allows you to trace objects. This one does finger joints, so if you want to make a box, you probably want to have finger joints in there. So we have a lot of specialized tools. And this combination, for example, I showed you here, allows people to make the simple gearbox. And notice the fact there was no computer involved here, you're interacting directly with the workpiece. We show you one more thing. This is a little booklet, and we actually took this on the road. We actually took this to Kai, and we also took it to the Tangible Embedded Conference, a laser cutter there, and people could try these things out there. So again, like here, the pull line tool gives me a chance just to make a little frame. I can round the corners, and you can see the laser. I don't know if you can see this. It just chops off the corners here. You just cross these edges, and then the laser cutter goes in and rounds the corners. And the last tool is a bend tool. It's actually my favorite. Right, there you go. Here's the little booklet. The bend actually allows you to bend the thing. You put like some receipts in, here's rubber band. And that's very similar to how we interact with touchscreens today, right? There's no one is sitting down in a terminal anymore. We work directly in a very direct way with the objects. Here's how we actually took this on the road. This is at the Tangible Embedded Conference here. We could make these things. So Constructible was limited though because it only did two-dimensional objects. That's the main limitation of laser cutters. I love laser cutters, they're very fast. And now actually curious again, has anyone ever used a laser cutter? Wow, okay. It's like more popular than 3D printers. Okay, you got on the right track, laser cutters walk. Okay, so we wanted to extend the system to also do 3D objects. And the question was, how can we do 3D objects? And here's our approach to it that we call laser origami. And as you notice, there's actually something, let me actually run this back. There's actually something in the laser cutter. So the object, do you see these little pins here? So the object is actually set down on a bunch of these prongs that kind of push it up. And so as before, we can cut using the laser cutter. But now what we're doing is we're moving the laser cutter down, and now the laser is defocused. So now here, you can see this getting transparent here. The laser is moving back and forth, but it can't cut anymore. It only heats it up because the laser is now blurred. And so what happens is, under the weight in its own weight, it starts to bend. And in this one process, we can both cut and fold. And so, I don't know if you recognize this, this is a camera holder for a mobile phone. And so normally if you would make this would take a couple of hours using a 3D printer. And with laser origami, this was a fast thing to do. We integrated this into standard packages like Visio, so you can just drag some of these bent components into your workpiece, and then fabricate things really quickly this way. Let me show you one more example just because I think it's fun to watch. So this is a little plant holder, and you can see the little arms in here. These are the arms that we're going to bend in a second here. So we're defocusing the laser. Now the laser goes around and heats up all these different things. Took us a long time to optimize that to actually work, reliably. So now we're done with this piece. We're moving back up. We're cutting it out. I really like this art because now it's actually dropping down. I think it's very satisfying to have the workpiece kind of fall out of the machine. And here's Stephanie's assembling this. And just to show that we're still computer scientists, she used a computer cable to mount this here.